Welcome back to the video lecture series of Digital Fundamental. Today we will discuss adders and subtractors. So let's start how we can design adders and subtractors. This digital computers performs varieties of operations, out of which binary arithmetic operations are most basic operations. Okay, and this addition is basically most basic arithmetic operations. Okay, this addition is basically most basic arithmetic operations. This addition can be performed by a circuit which is known as adder. Okay, adder is a combinational logic circuit which performs addition. Adder is a combinational logic circuit which perform binary additions. We have a two types of adder, that is half adder and full adder. What is half adder? So this half adder is basically adder which performs addition of 2 bits. Okay, which performs addition of 2 bits. Using this half adder we can perform addition of 2 bits. Here in this half adder we have 2 inputs and 2 output. These numbers organ and added bits are basically known as our input variable, and it produced sum and carry. Okay, so we have 2 inputs and 2 output. Here we can make a table for half adder. So here we have 2 input A and B and 2 output sum and carry. Okay, sum and carry. So here we have for a 2 input variable we have a total 4 possible combinations. So we can write a table like this: 0 0, so 0 1 1 0 1 1, so 0 plus 0, sum 0, carry 0, 0 plus 1, sum 1, carry 0, 1 plus 0, sum 1, carry 0, and 1 plus 1, sum 0, carry 1. Okay, so this is how we can make a table for half adder. So using this truth table we can identify or we can calculate equation for sum and carry, then we can design half adder. Okay, so here this sum is having a equation, that is a dash b plus a b dash. So basically this is XORing operation, so we can write like this: a XOR b. And for sum and for carry we have a equation a dot b. Okay, so for carry we have a equation ab. So we can implement this half adder with this logical function. So here we have a logical diagram of half adder: a b XORing, so we have a sum, and a into b and operation, so we have our carry. So this is half adder. Now what is full adder? So full adder basically adder which perform addition of a 3 bits. Okay, this full adder is basically adder which perform addition of a 3 bit, out of which 2 bits are basically our numbers, and this third bit is basically a previous carry. Okay, third bit is basically a previous carry. So if we have a and b 2 numbers, okay, 1 bit numbers, and here we have a c in, that is our previous carry. So here we have a 2 output, sum and output carry. Okay, so here we have a table for this full adder. We have here 3 input conditions. So for 3 input conditions we have a total 8 possible combinations. So here we have a b c in, and we have an output, that is sum and carry. So we can add these values like 0 plus 0 plus 0. So we have a sum 0, carry 1, then 0 plus 0 plus 1. So we have a sum 1, carry 0, and so on. Okay, so we can mark all the entries like this. Okay, and then we can identify or we can calculate equation for sum and carry. So here we calculate equation for sum, we write the values of sum or equations in which there is a 1. Okay, so we have equations for sum like this. We have here this a dash b dash c in plus a dash b c dash in plus a b dash c dash in plus a b c in. Okay, so if we simplify this equation, so here we have this kind of condition which is a xor b xor c. Okay, so here we have a conditions for sum, that is a xor b xor c in, and we can also identify the equations for carry. So here we have a equation for carry. Okay, we can write equation for c in like this, and this can be simplified like this. So a into b plus a xoring b into c in. Okay, so this is our carry equation and sum equation. So by considering these equations, we can design full adder circuit. So here we have a full adder circuit. We can design full adder with 2 half adder and 1 OR gate. Okay, we can design full adder by designing this 2 half adder plus 1 OR gate. Okay, so here first half adder. So here we have this a b xoring and a into b. Okay, and this xor output is given to next xor. So here we have a xor b xor c. Okay, so here this produced sum, and if we consider this a xor b, and if we apply our a and b into output, okay, so here we have a carry and then we OR this. Okay, so here we have a AB plus a xor b into c in. Okay, so this is our full adder by means of 2 half adder and 1 OR gate. So this is full adder. Now let's discuss about subtractor. Subtraction is another most basic arithmetic operations. Okay, subtraction is again most basic arithmetic operations. This subtractor is a combinational logic circuit which performs subtractions. Okay, this subtractor is a combinational logic circuit which performs subtractions of binary digits. Again, we have two types of subtractor, that is half subtractor and full subtractor. So let's discuss first half subtractor. Half subtractor is basically a subtractor which performs subtraction of 2 bits. Okay, subtractions of 2 bits. So here we have 2 numbers. Okay, that is a and b, and here we have 2 output, that is difference and borrow. Okay, in a subtractor we have 2 output, that is difference and borrows. So here we have a table for half subtractor. 2 input a and b. For 2 input conditions we have 4 possible combinations, and here we have a difference bit and borrow bit. Okay, so for this subtractor, 0 minus 0, difference 0, borrow 0, 0 minus 1, difference 1, borrow 1, 1 minus 0, difference 1, borrow 0, 1 minus 1, difference 0, borrow 1. Okay, so this is how we can make a table. Okay, now write the equations for this difference and borrow. So here we have equations for difference and borrow. For difference, again we have a dash b plus ab dash, that is a xoring b, and for borrow here we have equation a dash b. Okay, a dash b. So we can say that by inverting second condition, second inputs, we can convert subtraction into addition. Okay, because in addition we have a carry in which we have a equation c is equals to ab. Here we have a borrow, that is a dash b. Okay, so here by complementing this next bit, we can convert adder into subtractor. Okay, so here we have a logical diagram of half subtractor a xor b, and we invert a here. So here we have a NOT gate a dash and b. So this is our borrow. So difference and borrow. This is our half subtractor. Now next we have a full subtractor. Full subtractor, that means subtractor which performs subtraction of 3 bits. Okay, which performs subtraction of 3 bits. These 2 bits are our number, and the third bit or says third number is basically previous borrow. Okay, third bit is basically previous borrow, and again here we have a 3 inputs, that is a b and previous borrow which is bi, and we have a 2 output, that is difference and borrow. So here we make a table for this full subtractor, we have a 3 bits A, B and B in. That is our previous borrow, and we have a 2 output, difference and borrow. Okay. So here for a 3 input conditions, we have a total 8 possible combinations. So we mark all the combinations and then write the values of difference and borrow, like 0 minus 0 minus 0. We have a this difference 0, borrow 0, then 0 minus 0 minus 1. So 0 minus 0, 0, 0 minus 1, difference 1, borrow 0 and so on. Okay, so this is how we can calculate all the values over here, and then we write logical expressions for this difference and borrow. So here we have a logical expressions for difference and borrow. Okay, so we can write our difference equations like this, and then we can simplify this. So we have a term that is A XOR B XOR B in. Okay, so this is our difference equation, and next here we have our borrow equation. So if we write our borrow equations like this, so we can simplify this. So this basically A B plus A XOR B dash into B in. Okay, so this is our difference and borrow equations. By considering these equations, we can design a logical diagram of full subtractor. So here we have a logical diagram of full subtractor. Here we have a XOR B, first XOR, and then we use next XOR. So here we have a XOR B in, and here if we multiply this A dash B. Okay, so here we have this term A dash B, and if we here again use NOT gate, so here we have A XOR B dash, and then we OR this. So here we have a equation of borrow, that is A dash B plus A XOR B of dash into B in. So this is our full subtractor circuit. Thank you.